Experience in jungle campaigns has shown that the Japanese field fortifications, camouflaged by the rapid growth of the natural jungle flora and the Japanese continued resistance in a suicidal way after the military decision has been reached, sometimes makes the conquest of the Japanese-held islands costly in personnel and time. The Chinese, with hardly the bare necessities for combat, and frequently without any gas protective equipment, have, it has been reported, been subjected to several gas attacks by the Japanese. Although warned that the use of gas against the Chinese would bring retaliation by our armed forces, the Japs have persisted in such practice when hard pressed. Since the United States and England are not signatories to a treaty with Japan prohibiting the use of gas, and since the Japanese have ignored our warnings, no ethical reason is involved, and therefore it is only a question of determining whether or not it is to our advantage to initiate chemical warfare. To this end, the San Jose Project was initiated. The Japanese resorted to the use of gas against the Chinese only when hard pressed. Our forces are putting increasing pressure on the Japs to a degree not possible by the Chinese army. When driven to desperation, the Japanese reaction against our troops has been a frenzy of attack without thought of the cost to themselves. Illogical and unpredictable, they may resort to gas warfare without considering the cost. In that event, what will be the net result? These and many related questions demand carefully checked, accurate answers. Our own chemical warfare service had little experience in testing chemical agents, weapons, and protective equipment under tropical conditions. So it was proposed to set up a complete, coordinated plan of tests designed to furnish field commanders with the best obtainable data on protective equipment under tropical conditions, and also data on the behavior of chemical agents in case it becomes necessary to retaliate or the decision is made to initiate gas warfare ourselves. It was the decision of the Inter-Allied Chemical Warfare Committee that it be a joint project under the direction of an American officer. General William N. Porter, Chief of the Chemical Warfare Service, assigned General E.F. Bulletin to direct the project, and officers with military as well as technical background were chosen to staff it. English and Canadian Army officers and Royal Canadian Air Force officers were also assigned to the project. At preliminary conferences in Washington, experimental work done by the British at their chemical warfare jungle proving grounds near Innisfail, Australia, and Rawalpindi, India, was carefully studied while the test program was being prepared. During the planning period, the Navy and Marine Corps checked on the program of tests, and the Navy furnished 4 officers, including 3 aerologists who worked with the Air Corps meteorologists on micrometeorology. The NDRC offered its services, and the project was very fortunate in having 28 civilian scientists from Divisions 9 and 10 under the able leadership of Dr. Blasé of the Northwestern University laboratories attached to it. These gentlemen had been working in conjunction with the Chemical Warfare Service at Dugway Proving Ground, Utah, and Bushnell, Florida, on similar work, during which time they had developed new instruments and a technique for measuring gas concentrations to a degree and accuracy not before obtainable. Without their able assistance, it would not have been possible to obtain much of the highly technical data which is in the written report and on which many of the conclusions are based. After a survey of the Southwest Pacific Theater and the Caribbean area, San Jose Island in the Perlis Group was selected as the test ground, since the climate and flora are similar to that which has been found in the Southwest Pacific, and supply and availability of aircraft were more satisfactory. This island, which has not been inhabited since 1871, is covered with virgin jungle. San Jose Island is 7 miles long by 4 miles across at its widest point. The main ridge line of the island runs north and south up its longest dimension and attains a height of about 400 feet at its highest points. Parts of the island are broken and quite rugged. There is some difference in flora on the east and west slopes. In general, the eastern slope contains large trees and has a high jungle canopy, while the western slope does not contain many large trees and is a tangle of bush and vines at ground level. The island's flora is said to be typical of secondary forests found in the coastal areas of the larger islands in the East Indies and Burma. There are a few small tidal swamps on the island, and the weather is said to be similar to the Southwest Pacific area. So it is believed that the data obtained by these tests can be relied on to furnish accurate information on which to base plans for possible future gas operations in areas covered by tropical jungle. New Orleans was designated as the port of embarkation for both personnel and supplies. The bulk of the personnel and munitions to be tested, testing equipment, and test animals were shipped to Balboa Canal Zone and there transshipped by barge and small steamer to the island. In order to conserve time required to build a dock, supplies were landed by barge, taking advantage of the large tides that exist in that area. Approximately 30 miles of roads and 60 miles of trail were put through the jungle to enable munitions, sampling equipment, and animals to be moved to the test areas. Part of these roads, by necessity, had to traverse rugged country. A campsite was cleared of jungle and a sanitation and insect control plan initiated to ensure that work would not be slowed down by loss of man-hours from sickness. A field toxic gas handling yard was established and a refrigeration plant installed for storage of Class 1 supplies, which were delivered twice monthly, and for the storage of photographic materials and other technical equipment, which would have otherwise deteriorated under tropical weather conditions. The 6th Air Force made the bomber squadron stationed on the Rio Hatta Strip available for drop tests. This field was within 60 miles of San Jose Island. Therefore, all air munitions intended for drop tests were stored in field dumps in the vicinity of the runway. The Royal Canadian Air Force made a Baltimore bomber available for testing United Kingdom air munitions, which cannot be accommodated by our bomb racks. The organization of the personnel for carrying on the investigations included the technical group, made up of civilian scientists from the NDRC and technically trained Army, Navy, and United Kingdom Army officers, which conducted the tests, and a command and staff group which evaluated the technical information from the user's viewpoint. During the series of experiments, the technical group presented the results of each test to the commander of the project and his staff, on which were included the liaison officers from the Army Air Forces, Navy, and United Kingdom. Conclusions were reached and recommendations formulated at these conferences. Representatives of the using arms and services have concurred in all reports. Mustard gas is the defender's best agent in the tropical jungle. As the Japanese are on the defensive, we must continually advance through dense vegetation to get at them, and therefore our first series of tests was designed to discover how effective our protective equipment would be against that agent in both liquid and vapor form. To begin with, the ability of our troops to wear this equipment for long periods was tested. Some doubt had been expressed as to whether the wearing of impregnated clothing and protective ointment could be endured in the tropics. In this test, an infantry company from the Mobile Force Panama Canal Department wore ointment and impregnated uniforms in a two-sided free maneuver lasting 13 days. The men wore this equipment for 7 days and nights without removing their uniforms. 2 pairs of socks were issued and were alternated each day. At the end of 7 days, the men were allowed to remove their uniforms for 2 hours and take a bath, after which they put the same impregnated uniforms and socks back on and wore them for an additional 6 days. Each day, the men were checked for signs of skin irritation caused by the impregnated clothing. They were questioned as to the degree of discomfort due to such skin irritation as was found. The final check showed that the impregnite has some irritating effect. While annoying, the irritation was not sufficiently severe to cause any of the men to fall out during the maneuver. At the end of the 13th day, all the men stated that they felt they could continue in the field wearing the same uniform. The protective ointment was found to be soluble in the mosquito repellent, which had to be used each night. This is a serious defect as the soldier removes the ointment as he applies the repellent. However, this can be remedied by making the repellent the solvent for the active ingredient of the ointment. Thus, the repellent and ointment can be applied together without losing the effectiveness of either. Men were dressed in 1 1/2 thicknesses and 2 thicknesses of impregnated coveralls, which are less irritating to the skin than 1 thickness. Any added discomfort due to greater warmth appears to be negligible. Having established the wearability of protective clothing, the degree of protection it offers under tropical conditions was next tested. Men were sent through the jungle in the presence of mustard gas vapor and liquid. It was established that 2 layers of impregnated clothing will give complete protection against any concentration of mustard gas vapor that it is practicable to set up in the field. On the other hand, there is a hazard from liquid mustard gas in the jungle for about 3 hours after a bombardment, against which the impregnated uniform will not give protection. From a long series of these tests, it can be generally stated that 6 hours after a mustard gas bombardment, men with impregnated uniforms can enter and occupy with safety a contaminated area in the jungle, while troops without impregnated clothing cannot occupy the same area for 48 hours without expecting casualties. This series of tests was designed to answer 2 questions. First, when firing or dropping persistent gas munitions on jungle-covered terrain, what effect, if any, has the thick jungle growth on the functioning of fuses on both ground and air munitions? Second, what is the value of the gas liberated? The air munitions tested were the M70 100-pound bomb with the M110A1 fuse and the M47A2 100-pound bomb with the M126A1 fuse. Single bomb static tests were first made to determine the spread and vapor concentrations the munitions will set up in the jungle. The bombs were exploded at various heights above the ground to determine whether there would be any loss in contamination and vapor yield as a result of tree bursts. It was found that tree bursts up to a height of 25 feet gave highly satisfactory results, with diminishing returns up to 40 feet. Tree bursts above 40 feet were quite ineffectual. Small-scale drop tests established the probability that bombs dropped below 3,000 feet should be fitted with delay fuses in order to reduce the number of high tree bursts. On the other hand, it was established that the great majority of bombs dropped from 3,000 feet and above with instantaneous fuses would probably function satisfactorily. Final evaluation of the munitions was made in squadron drop tests from altitudes above 3,000 feet. Intervals between ships and intervalometer settings were selected to give contamination densities of 50 and 100 tons per square mile with each munition. In these final tests, chemical sampling instruments and test animals were both used. However, since mustard gas is somewhat more active and the human skin probably is more sensitive under tropical conditions, false conclusions might have been reached had results been judged on a comparison of chemical sampling data with physiological effects obtained in laboratory tests in the States. Therefore, final results were checked by the effect of the gas on personnel whenever it could be done without endangering their lives. About 500 bombs were dropped from above 3,000 feet, and the number of high tree bursts was negligible. Both munitions functioned in a highly satisfactory manner. Mustard-filled shells of the 4.2-inch chemical mortar and the 105-millimeter howitzer were also tested. Each munition proved to be satisfactory. Due to the greater capacity of the 4.2-inch chemical mortar shell as compared to the 105-millimeter howitzer shell, fewer rounds are needed to lay down the same quantity of mustard gas. However, the greater range and flexibility of fire of the 105-millimeter howitzer makes it a valuable weapon for this purpose. The vapor yield from both the air and ground munitions is high under tropical conditions. That is, on jungle-covered terrain with high humidity and high temperature. Judging from what is known of the physiological effect of varying concentrations, a comparatively light contamination density of only 50 tons per square mile will cause serious casualties to the majority of troops protected only with the gas mask, as are the Japanese, if they are in the area within 3 hours after the bombardment. On the other hand, this high vapor yield makes the gas less persistent, and it would be safe for completely unprotected troops to traverse the area 48 hours after the bombardment. This whole series of tests indicated that with present persistent gas-filled munitions on jungle-covered terrain in the tropics, the vapor effect for the first 6 hours will be very great, but that no present standard U.S. munition is very persistent under tropical conditions. Non-persistent gas can be used with less restrictions by an army on the offensive. As we are constantly attacking in the Pacific theater, this series of tests was planned with a threefold purpose. First, to compare the effectiveness of phosgene and the new gas CK under tropical conditions. Second, to test the functioning of both air and ground non-persistent gas munitions on jungle-covered terrain. And finally, to test the practicability of breaking Japanese gas mask canisters with CK and the determination of how our own latest canister stands up to this gas under tropical conditions. These tests started by assessing the relative values of single bombs filled both with phosgene and the CK gas, as to initial concentration setup, drop-in concentration with the travel of the cloud, and in canister penetrating properties. Gas concentration recording instruments developed by the NDRC in the laboratories of the California Institute of Technology made it possible to arrive at a more accurate determination than was formerly possible. Unmasked goats and goats protected by masks fitted with Japanese and German, as well as British and our own canisters, were used as a check. Canister tests were made also with the mechanical breather, which draws air through a canister in the same average quantities and at the same average number of inhalations per minute as does a man. From these initial tests was determined the desired spacing of bombs to maintain a lethal concentration throughout an area. The best ground pattern was worked out and checked by small-scale multiple bomb static tests. These results were translated into Air Force operating procedure. It was established that phosgene is much inferior to the new gas CK in the jungle, as phosgene is quickly absorbed by the lush jungle growth and the concentration drops off quite rapidly as the cloud travels. On the other hand, very little CK is lost by absorption, and therefore its cloud has a greater range of travel at an effective concentration. Final results of the air munitions were judged on 6 drop tests conducted by a squadron of B-24 bombers of the 6th Air Force operating from the Rio Hatta Strip on the Isthmus. Bombardments were conducted for each agent on 6 consecutive days under varying weather conditions. The overall picture thus obtained established beyond reasonable doubt the superiority of CK over phosgene on jungle-covered terrain. After each shoot, the recorded concentrations and the results on test animals were plotted on a map of the target area. From studies of this map, it was determined that a given amount of CK will produce a lethal area about 3 times the size of the lethal area which can be set up by a like quantity of phosgene. On concentrations that can be set up in the jungle, the canister breaking quality of the new gas CK was very pronounced. The Japanese canister proved to be the poorest one tested. Goats wearing the Japanese canister were killed by the new gas CK when tied or penned on the surface of the ground. Finally, dugouts were gas-proofed by usual field methods, and goats wearing Japanese canisters were placed in them behind gas-proof curtains. Within a few minutes after the cloud of CK reached the dugouts, it had penetrated the gas-proofing, broken the Japanese canisters, and killed the goats wearing them. On the other hand, the ability of the latest U.S. canister to resist CK in concentrations practicable to set up over any considerable area was well established. CK-filled ammunition was tested in the 4.2-inch chemical mortar to determine whether the characteristic of the munition was suitable for such a filling and to study the munition's functioning. 2 night bombardments were fired on the same target with weapons of a chemical combat battalion during favorable weather conditions on 2 successive evenings. Each mortar fired 35 rounds in each bombardment. The test was held in the middle of the rainy season, and some difficulty was encountered in keeping the mortars accurately laid in the soft ground for a burst of 35 rounds. As this condition may often be expected in the tropics, valuable data in technique was acquired. Even with the mediocre performance of the mortar mounts due to insufficient backing for base plates, highly satisfactory results were obtained. The impact area consisted of 4 artillery squares, over which and around which sampling instruments and test animals were placed. By impacting on 4 artillery squares, a canister breaking concentration was set up on 12 squares and a lethal concentration on 38 squares. The effectiveness of such a weapon is apparent against troops dug in or in caves and safe from everything except direct hits by HE shells equipped with delay fuses. By firing CK on a target of 4 units in area, a Japanese canister breaking concentration would be set up on an area of 12 units, which is 3 times as large. And on an area of 38 units, or 9 1/2 times the size of the impact area, a lethal concentration would be set up which would kill a Jap whose mask leaked or who failed to get it on in time. From these tests of both air and ground munitions, it was established that CK is a very effective agent in the jungle. And in considering the relative ability of the Japanese gas mask and our own gas mask to protect against CK, it is apparent that even if the Japanese have this new gas, its use by both sides would be to our advantage. This can best be illustrated by a close-up view of the effect of this gas. Cameras were placed at close range to record what happened and were operated by remote control from a safe distance. The goat on your left is equipped with a U.S. Army canister containing charcoal which has been treated with the ASC catalyst, the method of treatment and formula for which are secret. The goat in the middle is wearing a Japanese Army canister. The goat on your right is unprotected. The middle goat with the Jap mask refused to face the firing squad, as you can see. He is only sulking and is just as healthy and just as much alive as the others, for the time being. Now the new gas begins to break the Japanese canister. Both the unprotected goat and the middle goat wearing the Jap canister were killed by the CK. Protected by his U.S. Army canister, the goat on the left was unaffected. He was placed in the veterinary hospital under observation for 3 days following the test, during which time he developed no ill effects. thus proving that Allied troops protected by the latest U.S. canisters would be unharmed by a concentration of CK sufficient to penetrate Japanese canisters and cause heavy casualties. It's well understood that gas would be of small value against ships in action due to the wind velocity caused by their movement and their evasive maneuvering. In addition, personnel inside the vessel's hulls are given excellent protection against gas by the air recirculation systems. On the other hand, a gas attack could be directed under favorable conditions against exposed personnel on a stationary ship. Such an attack might be feasible against the Japanese fleet if it avoids further decisive action at sea and is bottled up in a fortified harbor. In our test, then, the ship will be stationary, and the test will determine this. Can non-persistent gas be put down to cover an entire ship, including its tops, in sufficient concentrations to make instant casualties of the anti-aircraft gunners? If so, an air torpedo or dive bombing attack could be pressed home immediately after without the probability of serious losses to the attacking planes. In selecting material for the test, it is obvious that the impact fuse used on gas bombs against land targets would be unsatisfactory against a ship target. The cooling caused by the quick expansion of the concentrated gas leads it to mushroom and flatten out. Frequently, the heavy concentration of the cloud is not over 10 feet high. Thus, while it would be effective against land personnel in dugouts and foxholes, the low cloud would not ensure casualties among gunners stationed above a ship's main deck. Bombs with the same fuse dropped for water impact give an even less satisfactory result. In addition to the low cloud, most of the gas is removed from the air by the washing effect of the splash. An airburst fuse must be employed to create a cloud deep enough to cover all a ship's exposed personnel with lethal concentrations. Using the T-51 and the T-50E4 airburst fuses, the test begins. A series of 6 separate trials are flown by a single plane to establish the height of burst and to study the characteristics and travel of the gas clouds liberated. 8 bombs are dropped on each trial. First a raft, then a barge, both stationary, are the targets. The bombs are dropped singly and in 2 and 4 bomb trains. From these tests, it is established that the T-51 fuse is superior to the T-50E4, that the average height of burst is about 75 feet, that the gas cloud does not immediately drop and mushroom, but remains as high as the superstructure and tops of the ship for some minutes. We're now ready for the final test. The target is a ship's hulk with 2 barges moored to its stern, 700 feet overall. This gives a length of target equal to the Nagato class of Japanese battleship. From a tug, goats are loaded onto the target ship to represent Japanese personnel. 10 testing stations are established on the ship at locations where anti-aircraft weapons would be expected. The stations are placed at bow and stern, at different locations on the main deck, and at varying heights above it. Each station consists of a gas concentration sampling instrument, 1 unprotected goat, and 1 goat protected by a gas mask fitted with a Japanese Navy gas mask canister. Several unprotected goats have been placed on a guard boat, which takes its place 800 yards downwind of the target ship. CK non-persistent gas is used in the 1,000-pound bombs. "11 B-24 bombers make up our squadron, to which are attached 2 planes for observation and photographic purposes. The bombs are dropped from a height of 12,700 feet. 73 bombs are dropped by the 11 planes, each plane dropping in train at 50-foot intervals. The 11 fuses give ineffective high bursts, and the bomb release mechanism of one plane initially jams, causing a delayed and ineffective oversalvo. The gas cloud completely covers the target, horizontally and vertically. Its duration on the ship is 16 minutes in low variable winds not over 2 7/10 miles per hour. On the target ship, all unprotected goats, no matter where stationed, are killed. Also, all unprotected goats are killed on the guard boat stationed 800 yards downwind of the target ship. 30% of the masked goats are killed. The sampling instruments record that concentrations several times that which is considered lethal were set up throughout the target, thus indicating that this form of gas attack is feasible as a preparation attack to neutralize anti-aircraft fire immediately preceding an air torpedo or dive bombing attack. From this program of tests, the following conclusions are reached in regard to defense against chemical warfare. First, that protective ointment and 2 layers of impregnated clothing are bearable in the tropics and will not cause undue skin irritation. Second, with very little modification, the ointment can be made into a combination gas protective ointment, mosquito repellent, and camouflage face paint, without impairing the efficacy of any one of the components. Third, it is necessary to wear 2 layers of impregnated clothing to give adequate protection against the high vapor concentrations of mustard gas which result in the jungle. Fourth, this protection cannot be broken by any concentration of mustard gas vapor which it is practicable to set up in the field. Fifth, however, no amount of impregnated clothing tolerable in the tropics will give adequate protection against liquid mustard under 3 hours after a heavy bombardment. Sixth, The U.S. Army gas mask canister filled with ASC charcoal is superior to all other canisters tested and will give adequate protection against the heaviest concentrations of CK non-persistent gas, which it is practicable to set up over any considerable area in the field. In regard to offensive use of chemical warfare, it is concluded, first, that all our standard gas munitions, both ground and air, are satisfactory for use on jungle-covered terrain. That CK as a non-persistent gas and mustard as a persistent gas are very effective under tropical conditions. Third, that the Japanese gas mask canister is inferior to all other canisters tested and will not give adequate protection against CK non-persistent gas. Fourth, it is concluded that non-persistent gas could be used successfully in a first surprise attack against the anti-aircraft personnel of an enemy fleet at anchor in preparation for an air torpedo or dive bombing attack. So, finally, the conclusion is reached that gas would be more effective against Japanese troops than against our own, and therefore, if gas warfare is initiated, it will be to our advantage.